So let's talk about the science beneath the photopolymerization process. So the photopolymers are cross-linked. So from this figure, you can see the difference between a uh, cross-linked polymer versus a non-cross-linked. So on the left-hand side, so as you can see, those polymer chains, they're not bonded each other. They're not linked each other. It They're just like spaghettis or noodles, right? But on the right hand side, you can see between these polymer chains, there are linkage over here. There are bondings between them. So this is the cross-linked polymers, and the photopolymers are cross-linked. Some good properties of this kind of polymers. Basically, it can, in general, resist solvent, which is a good property for many applications. Also, in general, it can bear high temperature than those thermoplastic. Basically, thermoplastic is not cross-linked, but the downside for photopolymer is it cannot be reprocessed. In other words, it cannot be reused or recycled once it's cured. But the thermoplastic can be recycled, as we mentioned in the fused deposition modeling process. Also, some very important parameters in the photocuring, which is the process of hardening a liquid resin via the selective applications of energies like UV light or infrared light, and so on and so forth. So the first parameter or factor is the penetration depth. Basically, when the laser scans the resin, liquid resin, there will be the material beneath the liquid surface be cured based on the energy intensity. So if we take the approximately 1/3 of the energy intensity decays as the standard and measure the depths beneath the liquid surface, then we get this penetration depth. Also, another important parameter is this scan velocity. It's very simple, just like what we have in the fused deposition modeling. It represents how fast you move the laser beam, right, to scan over the liquid resin. Another parameter is the critical exposure. So basically, it represents the energy per unit area needed to produce the gelation of the polymer or the curing of the polymer. So the last parameter is the cure depth. Basically, this cure depth is a function of all the above parameters. And it gives you the idea of, with these condition nodes, how much the depth is when the material is cured. This figure shows a illustration of the laser exposure in the resin. And here is an equation, EYZ. It gives you the laser exposure in the unit millijoule per centimeter or millijoule per millimeter. So basically, as you can see here, the horizontal axis is the y-axis, and the vertical one is the z-axis. And this equation gives you any location at a specific y and z, what is the laser exposure. And as I mentioned, it's the function of all these parameters. The laser power, the Gaussian half width of the beam. So basically, it represents this width. Also, the velocity of the beam and the penetration depth. Basically, for this Gaussian-like shape, let's look at this W0. Basically, it gives you the Gaussian half width of the beam, and at the same time, it represents the beam radius, right? What is the radius of the laser beam? And for any points in this region, if you substitute its y and z numbers to this equation, it will give you a laser exposure numbers, and that is very important. So if we look at this equation again, and some of them are the parameters or of a function of the laser or laser scan systems. And what are they? So first of all, this W, right? The laser power, and also I'm sorry, it should be this PL, which is the laser power, right? And also this let me erase this. And this Vs, which is the laser scanning velocity, right? So this is the these are controlled by the laser scanning system. And what are the parameters or functions of the resin you choose? So that is the penetration depth over here. Basically, at which the energy is sorry, it's not E, it's 3. It's 1/3 of the energy at the surface. And what is the depth beneath the liquid surface? Also, if we look at here, again, this equation, and if we increase the scanning velocity, that means we scan the resin faster. What's going to happen? So if this is larger, then the overall here will become smaller. So that means the laser exposure is smaller, which totally makes sense, right? So that means if you scan it faster, the resin is not cured sufficiently, and it gives you a smaller laser exposure. So if we increase this laser power, you could see intuitively this number will become a larger number, and the laser exposure is becoming larger, which totally makes sense again, right? So let's look at example questions. So with these conditions known, what is the laser exposure at a depth of 0.05 millimeter, which is the Z, and a lateral distance of 0.03 millimeter, which is the Y, from the center of the beam. So you could compute it by substituting the Y and Z and also these numbers into the previous equation, and you will have a laser exposure millijoule per square millimeters. So let me show you the result. So as you can see here, that's how you substitute all the numbers and also the Y and Z values to this equation. And it turns out you have something like this. It represents a certain number, I would say probably here, I don't know, probably some location here, and what is the laser exposure at this certain locations, right? Also, for this number, a very important thing is you need to compare with the critical energy EC and see whether this is larger than EC or smaller than EC. It tells you whether at this point the resin can be cured properly or not, which we can talk more in the next slides. So again, the EC is the critical exposure level need to be initiate the curing. So if the energy density is less than EC, that means there's no curing happens. And if, I mean, in other words, if you know the EC, you can determine the width of the cure line at the surface such that to make sure the material could be cured as properly. And here shows you a illustration of the different layers. This is the previous layers, and this is the next layer after the previous one. And the light source is scanned in this direction. See? And as you can see here, if you properly adjust the distance between each of the scanned lines, it turns out they will have a large area of overlap. And if you select an appropriate number, and then it will become a whole solid layers. But in most of the case, if the distance is not good enough, you will have some uncured empty regions like here, shown here. So let's look at the equation more. And as you can see here, there's a maximum cure depth. So this maximum cure depth gives you the idea what is the CD along this line when y equal to 0. That's the maximum cure depth, right? So when y equal to 0, it will give you this number, right? And also the maximum exposure energy, which happens right on this spot. When y equals to 0 and z equals to 0, it turns out when you substitute this to 0 to the equation, you will have only this number left. So as I mentioned, if you have a desired cure depth, which is represented by CD star, right? So you know this cure depth, and you want to determine what is the laser velocity. Then what you can do is you just substitute this desired cure depth into the equation and reform the equation to find out what is the velocity, laser scanning velocity Vs is. And that could be a question in the homework or exams. That is, given a cure depth, and tell me what is the laser scanning velocity. So there could be the curling and also distortion happens as shown in this figure. As we mentioned previously, there's shrinkage happens, so-called the curing shrinkage. Basically, when the material is cured, there will be a shrinkage generated. And that's why if you print something like this, a surface point downward, that could be some tilted shape or distortion happens. So you definitely want to find the material which has the least curing shrinkage such that you could avoid a large surface distortion when printing the part. Also, the photopolymers could be plated. Basically, they are quite good surface finishing if you plate the printed part. Use the electroplating process. And let's look at what are the steps for the electroplating of the photopolymerized part. So first of all, you just make your surface electrical conducting and brush on the silver paint. Chromic acid will etch the ABS plastic, and active surface in the palladium or a tin chloride to deposit conducting metals into etched surface. And then you just plate very thin electroless nickel. And then you can electroplating with the, you can electroplate with copper, brass, or other metals. Or and after that, you could further do another layer of plating or not. And it turns out you will have a full plated part for different applications as you need. So the biggest application for the photopolymerization-based 3D printing is this Invisalign braces. So first of all, the dental, the teeth 3D model is obtained by a 3D scanning process. Usually your dentist or the orthodontist will do the scanning for you in the clinic, and then with this 3D model, a series of corrected shape of your teeth is generated at each stage, and then use this shape. The Invisalign will print this 3D shape as the mold, and then they will do a thermal forming, use the polycarbonate or polyurethane sheet to form these final invisible braces, and then they will be delivered to the patients, and that's how it worked for the whole process. And I will let you watch this video about how it's made.
The idea of mass customization is really basis of the company's existence. The idea that originally sparked the whole thing was, can we use digital technologies to kind of bring the science of teeth straightening into the next generation? When Invisalign started, 3D printing was primarily used for prototyping, limited number of parts. So what we had to do is really figure out how to make that into a production process.
3D printing is really kind of the foundation of our manufacturing process. It's the starting point. When we make a mold for every stage of a patient's treatment, we use 3D printing to make those molds.
If you think about an injection molding type of process, where we're only producing the same type of part, millions of those, so that's been done before. Or you think about a very specialty 3D printing application where each part is unique, but they're produced in a small quantity. What we've done at Align is really combine those two. We've treated almost 6 million patients, and the growth is actually accelerating. We produce about 320,000 parts every day.
From a support perspective, 3D Systems has been instrumental in helping us get to where we are today.
What makes Align's mass customization so unique is not only are we producing millions of parts every month, but each one of these parts that we produce is unique. And this is really the, as far as I know, the only true example of mass production using 3D printing.
All right. Let's move on. Okay, another widely used application for the photopolymerization-based 3D printing is this customized hearing aid bar. So basically, first you need to take the scanning of your ear canal, and then design the customized hearing aid using these scans, and then you 3D print it using the stereolithography-based or other photopolymerization process, and then color it, paint it, and assemble the printed shells with the electronics part. And it turns out you will have a fully functioning hearing aid buds.